President of Human Resources and Administration, and also Acting Vice President of Operations. We are honored to be joined this evening by the Director of New York's Hayden Planetarium and host of Fox TV's Cosmos, The Space-Time Odyssey. He is a world-renowned author and astrophysicist, and when it comes to cosmic phenomenon that requires explanation, he is the go-to guy. Please, everyone, give a warm welcome to Dr. Neil deGrasse.
You guys can hear me just fine?
I'd like to thank you so much for joining us tonight. Thank you so much for being here with us.
And you guys can hear me?
We can hear you just fine, and we can see you too.
Excellent.
Thank you so much for being here with us this evening. We have a very excited crowd of visitors here at the Space Foundation Discovery Center. It includes, I'd like to just familiarize you with your audience, it includes general admission visitors to the Space Foundation Discovery Center. It also includes Space Foundation team members, many of whom you have met before when you visited the Space Symposium. It also includes a group of 11 interns from high school level that are sponsored by Lockheed Martin. And I want to call to your attention that several of those interns were second in the world in the International Space Settlement Design Competition. So we're among very esteemed company. And we also have several here
Wait. Why weren't they first in the person? I'm leaving. I don't know.
And we also have several educators here that are participating in our astronomy workshop this week. So welcome to all our audience members as well. We have collected a number of questions, Dr. Tyson, and I'm sure that we won't have time to get to all of them. But I will start off with the first question that has been posed by the Lockheed Martin interns, which I'll remind you are high school students.
Wait, so I will not get to hear the question asked by the person.
Well, the group is a group of 11, so I am going to pose this question on their behalf, if that is all right with you, sir.
Okay.
Thank you. The first question, sir. How will the dependency of new generations, and to some degree, the apathy caused by that dependency, pose problems in the future?
Wait, could you repeat that?
How will the dependency of new generations on technology, and to some degree, the apathy caused by that dependency on technology, pose problems in the future?
So what you describe becomes a problem only when technology ascends and then plateaus. And then everyone becomes complacent with the level of technology that has been. But we have been, in fact, strongly impacted by the advance of technology ever since the Industrial Revolution. I have a set of books that I read often that reflect on the magnitude of the changes that had occurred in the recent years at that time. And you could read this going back deep into the 1800s, when railroads were first enabling cities to be connected. And then later in the 1800s, the invention of the telephone, 1876. All of a sudden now, people could communicate with one another, and their lives were changing. We look at that as quaint today, but at the time, people could not stop talking about it. The development of the telegraph, the invention of the internal combustion engine automobile, airplanes. So our lives have been changed radically since the dawn of the Industrial Revolution. So the complacency comes about if your technology doesn't keep advancing. If it keeps advancing, we can still be surprised and shocked and amazed and write about the new developments that come our way. But the moment you stop advancing, then, yeah, complacency kicks in. You take it for granted, and I don't know that anyone is thinking that they should keep moving it forward. What is their motivation? I don't know at that point. And so often it's economic, obviously. The great next invention makes the next billionaire. But we're complacent about flying airplanes. You can get in an airplane, fly at 37,000 feet at 500 miles an hour for 2,500 miles from New York to Los Angeles, get off the plane, and complain that the meat was overcooked. That's complacency about air travel. You are completely ignoring what just happened to you and worrying about the minutia that's surrounding it. So we've been complacent about a lot of things over time. I don't have a problem with that. As far as I'm concerned, keep the innovations coming. That'll keep me happy.
Excellent. Thank you, Dr. Tyson. Now, if I may, please, to go along with what Dr. Tyson said, we would like for Hunter Parkhill, 13 years old. Are you here, Mr. Parkhill? Would you please come forward and ask your question of Dr. Tyson? No pressure. No pressure.
Okay, so
If you'll speak that direct to the microphone there.
if wormholes could be created, or if they do exist, how can I help the science community to get them?
And you're 13?
Yes. Not today.
Sure. So our current capacity to travel through space is, we can praise the fact that we've been to the moon, but we need the occasional reminder that that took 3 days traveling to our nearest neighbor in space, itself 250,000 miles away. How long would it take to get to Mars? Well, a minimum energy transfer is a little less than a year, and then you got to hang out a couple of years, and then it's a year back. If you want to go to the outer solar system, you're talking about decades. Even though we've never been there, even if we could go by the methods of travel we can even imagine, it's decades. So if you want to travel the stars, it will take longer than the human life expectancy. And there's a rule in science that you never perform an experiment that will take longer than your life. You want to be around for the result. So if we're to go anywhere in the galaxy, we will need to have a new understanding of the fabric of space and time. And that would require some kind of access to wormholes. We don't know how to make them. We don't have access to the energy required, even in the equations of physics that allow it. And once we make a wormhole, we don't know how to keep it propped open. We think we can make one and it'll be open like just long enough for you to get in it, and then it'll collapse around you, no telling what's going to happen to you when that happens. So you want to know how you can help. I don't know how you can help. The wormholes we got them theoretically. We understand pretty much the physics of it. But to make a wormhole that'll get us to another galaxy will require the energy, as far as we understand, require the energy of all the stars of an entire galaxy. And right now we are fighting wars to get access to fossil fuels buried beneath the sands of other countries. So we are nowhere near have the control and power over energy to even have those dreams. So I don't have a good answer for you. I know, maybe you'll be the person who will invent the warp drive. It was an entire episode in one of the films of Star Trek where they go back to the guy who's inventing the warp drive, which completely transformed space travel for the science fiction series Star Trek. So, but we don't even know how you would do that. So I can't be more encouraging.
Thank you, Hunter. Great question. How about Ingrid Daniel? Making her way up, Dr. Tyson.
She's orbiting.
I'll have you know that Ms. Daniel has been in here since 3 o'clock, faithfully watching episodes of Cosmos in anticipation.
My question for you, sir, is will you talk more about the Drake equation in your Cosmos episodes as Dr. Sagan did in the original series? And has scientific thinking changed regarding any of these variables in this equation since the original series aired? And thank you for taking time to talk with us today.
Sure. So the Drake equation, as some of you may know, it's often thought of as a. You guys can hear me? Good. You can hear me?
Yeah, we can hear you. We had to mute our microphone because you were cutting out, sir.
Oh, that's what that was. Okay. I'm going to mute mine as well. Okay. The Drake equation, for those of you who may not be familiar, there was an American astronomer, although getting along in the years, his name is Frank Drake. And he was one of the early pioneers, along with Carl Sagan, among the thinkers of what it would be like to make contact with extraterrestrial intelligence. And so he proposed an equation to estimate how many other intelligent aliens might be out there in the galaxy. And that equation is not so much, it's not a formal mathematical equation where you have an unknown and then you have an answer and you plug one. It's more an organization of our ignorance. You start out with things maybe you have a good handle on. At what rate are stars being born? Because we think if we're going to look for life, it's going to be on a planet orbiting a star. So let's find out how many stars there are out there. What's the rate that they're being born? Okay, and then you start out approximately how many planets per star are there. So you throw in a number. Is it 10? Is it 5? Is it 50? Throw in 10. We have 8. 8. So throw in 10. And so, all right, so now, all right, we think life needs the Goldilocks zone. That play not too close to the star, not too far away. Too close, if you had liquid water, it would evaporate. And too far away, it would freeze. And life as we know it requires liquid water. So not all the planets are going to be in the zone. So you had to pick a number. And back in the original cosmos, we had no data on planets outside of our solar system at all. So we had to make guesstimates there. Right now, we have a catalog of 1,000 exoplanets. So we have some good data to put in those first set of fractions. Okay, so what fraction of stars with planets have planets in the habitable zone, the Goldilocks zone? Of those, which of those might have had life at all? And of those with life, which of those develop intelligent life? And of those that develop intelligent life, which ones have reached a technological state where they can transmit signals on purpose across the galaxy? Those are the ones you're looking for to make contact with. In the current cosmos, we threw a bone to the equation. We didn't bring in the equation in all of its glory. Most of the early terms we think we have a good handle on. But you know what the biggest uncertainty is? And we say this in the current cosmos. The biggest uncertainty is once you've achieved technological capacity to communicate, how long do you retain that ability? For example, do you annihilate yourself? Do you go extinct from your own power? That almost happened during the Cold War. If that were the case, we would have been radio communicative from the 1920s and 30s through 1965. 40 years out of the billions of years of the history of the Earth. So that'd just be embarrassing. Just right when you can be able to talk to aliens, you kill yourself. Okay, so we don't know what actual civilizations, what the longevity of an actual civilization will be with that capacity. Consider also that radio waves, which is what that penetrates through gas clouds in the galaxy, and we think we're pretty clever coming up with these. But maybe a super advanced civilization says, ha, 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 radio waves. That's how quaint. You need to use lepton rays or something. I don't know. Some other kind of communication we haven't even invented yet. So there could be some terms needed in there in the Drake equation that properly reflect our infancy and our ignorance of ways that could be out there where other aliens are having full conversation about their lives and who they're dating and new energy sources they came up with, and we are oblivious to the entire thing.
Thank you so much.
Next, let's have Mr. Ian Campbell step up. Thank you, Ian.
Alright, what proven theory did you find the most surprising?
Repeat that?
What proven theory did you find the most surprising?
Surprising. Surprising. I'll tell you a really cool one. It's just, I just have to pause every time I reflect on it and say, man, that's cool. That's good. That's good. Yeah, not just good, it's good. So quarks are only ever observed in pairs. We know the pair has 2 quarks in it. We can measure that. We've never found a single quark. And a quark are the basic elements, the basic constituents of protons and neutrons and other similar particles. So a proton has 3 quarks in it, a neutron has 3 quarks, and they're different kinds of quarks, which when they combine together, as they do, these 3 quarks combine make a proton, these 3 quarks combined make a neutron. And they have fractional charge. So they're really odd and bizarre particles, but they're real, we measure them, we know they exist. Now here's what happens. If you try to pull 2 quarks apart, you can try, but to do so requires energy, like stretching a rubber band. You're putting energy into the rubber band. Now, there comes a point where you keep pulling the quarks apart with such ferocity that they eventually snap apart. They will. But the moment they snap apart is the moment you had put so much energy into it that you have the exact amount of energy, according to E equals mc squared. E and m are on separate sides of an equal sign. I'm putting energy into these quarks. The moment I've reached sufficient energy, bam! Those 2 quarks that I just separated spontaneously create a pair of quarks for each. So this one that I pull apart, bam! A new quark gets created. Bam! A new quark gets created. Using the energy that I put into the system to separate them in the first place. So the act of trying to separate them creates another set of quarks. You're not getting one quark all by itself. That's just cool.
I do not have a last name on this, but Roy H. Where is Roy H? You submitted several questions. I only picked one.
How you doing, Dr. Tyson? First of all,
Good. Thank you.
First of all, it's an honor to be able to hang out with you. My question is, what important piece of advice would you give a young, aspiring future leaders in astrophysics and space discovery?
What level of year do you concern yourself with? Could be any year.
Oh, okay. I'll repeat my question. What important piece of advice would you give to young, aspiring future leaders in astrophysics and space discovery?
Yeah, I'm just wondering a bit young. Quantify that.
High school, I guess, high school, college.
Okay. So I would say that one of the interesting things about the physical sciences, physics especially, astrophysics is a branch of physics, is that on the frontier of discovery that they represent, the field is hard. There's a lot of math and a lot of branches of physics that come together that enable you to describe and understand how the universe works. And there's so many people who, when they go to high school or go to college, they have an urge to take easy classes. And what is an easy class? It's a class that everyone else takes and they all get high grades. Now, why does everybody get high grades in an easy class? Because it's easy. So if you take harder classes, maybe you won't even get the A. You might get a B, but you'll be exposed to much deeper understandings of nature. There's a great quote from President Kennedy where he said, "We choose to go to the moon, not because it's easy, but because it's hard." The hard paths are the paths of discovery. History has shown. Occasionally, a low-hanging fruit drops down, but someone's going to probably get that before you will, if it's low-hanging and everybody sees it. We're talking about the hard-to-get fruit, the ones at the top branches. And so I would encourage people, I would encourage you to not shy away from the hard classes. Embrace them, even if you have to struggle, because therein are the pathways to that boundary between what is known and unknown in the universe. And that's where you have to be standing to make a discovery. So work hard and embrace it. If you don't like the hard work, there's a lot of other easier things to do in this world. So you have to say, I like it because it's hard, not dislike it because it's not easy.
We have time for one last question, Dr. Tyson. And this one doesn't have a name on it, but why do you think our corner of the cosmos is or is not, or would not be, an interesting place to visit on the cosmic scale?
Sure. It depends what you mean by our corner of the cosmos. If you mean Earth, that's one thing. If you're talking about our galaxy or the part of the spiral arm of the Milky Way where we happen to be located, that contains the stars, which when we look up in the night sky, we trace constellations. That's our sort of local group of stars that are the solar neighborhood. We're all sort of orbiting the center of the galaxy together. You can think of that as our sector in the galaxy. But then there's our part of the larger universe. We're in a suburb of the Virgo supercluster of galaxies. So I think there's some points of interest. If I can imagine a future time where you might have create a travel log of all the interesting places to see in the universe, just as one might create the interesting places to see in our country or around the world. If you imagine our country, one of the stopping places would have to be somewhere in the Rockies. Why not Colorado? And so that's very different from the valleys and the oceans and the beaches. It's also very different from the rainy places, the rainforest. Seattle happens to be near in a rainforest latitude. So in Seattle, they hardly see the sun. And when they do, they all cut class and leave work and hang out in the parks. So they're very different parts of the country. So I think of the universe, there are places where stars have just exploded. There's places where stars are about to explode. There are places where stars are being born, stellar nurseries. We see these using special wavelengths of light with the Hubble telescope that can peer into these clouds of nascent stars, and so that would be like the in the hospital where all the babies are being born. That's a place to visit if you're visiting a country. And so there are stars being born. There are hot stars and cool stars, and they each have different sort of radiation coming out of them. That's kind of interesting too. The hot ones are blue. The cool ones are red. And some stars have planets. Many stars have planets. That's kind of interesting. What are those? Some are made of gas, some are made of rock. And so you come to our sector, there happens to be one of these rocks, the third one from its host star, where matter and energy have come together and made what we call life. And life now actually actively transforms its home planet. The humans are not the first to do this. Cyanobacteria, one of the earliest life forms on Earth, thrived on carbon dioxide and other chemicals. Its byproduct was methane and oxygen. Okay? Oxygen was a byproduct of the metabolism of this organism. So before the cyanobacteria came around, we could not have existed. They completely transformed our atmosphere, made it oxygen rich. That's kind of interesting. If you're a tourist of the universe, you might want to watch that happen and see as they're burping up the oxygen. And then there's some animals that die in the presence of oxygen. Others rise up in its place. And now we have a world thriving on oxygen, which is a little bit like rocket fuel for animals. And this oxygen is now in harmony, largely in harmony with the plant life. Okay, we have trees that give off oxygen, take in carbon dioxide. We thrive on the oxygen. That's an interesting place that's kind of interesting to me. Now, of course, we're biased. There's human hubris that says, we're interesting. Our planet is interesting. It may be that there are other planets out there that are far more interesting than we are. And some clever science fiction writers have imagined this. Perhaps there are planets with life based on silicon instead of carbon. They're carbon-based life. Perhaps there's planets where the life is not material in form. Maybe it's made of some kind of forms of energy. There's a science fiction story, I forgot the title, but I remember one of the punchlines, which may have also been the title. It's called, "They're Made of Meat." And it has to do with alien life forms that are made of some form of energy, and they come to Earth, and they find out that on Earth, the life on Earth is made of like flesh. And they say to them it's meat, because they eat it, and so, or they consume it. So the great challenge for us is imagining sectors of the galaxy that could possibly be far more interesting than anything we've ever dreamt up here on Earth. So to summarize, lots of awesome places to visit in the galaxy. We've kind of also sort of visited them with our images from the Hubble telescope. We visit them at safe distances. So sure, I mean, the travel log would be awesome. And our corner of the universe, I'd like to think that if we're visited, that we won't shoot them. All right, that would be there'd be a big, X in our sector in the cosmic tour guide book if that's how we treated visiting aliens. So there's a lot to think about there, and in fact, I think a lot of latitude for creative science fiction storytelling.
Thank you so much, Dr. Well, we so much appreciate the time that you spent here with the Space Foundation Discovery Center. We appreciate it very much. I'd like to thank Brian DeBates, who hooked up our Google Hangout, and also Mike Melroy, who was our tech support. We've also had a lot of support from other Space Foundation team members, so my thanks to them. And once again, Dr. Tyson, thank you so much. We appreciate it. And thank you to all our visitors. Good night.
Okay, guys.